480, then L1, L3, 480.
Hey guys, I'm headed out to the west side today. I got a follow-up with a trouble call I did about maybe a week ago. We have two large transfer pumps set up. There's no utility power available at the site. There will be in the future, but for now there's not. There's no utility power at the site. They're currently using, I believe it's a 300 kilowatt generator, 480 volt. It's wired into an MCC with two VFDs. I believe our motors are 125 horsepower, if I remember correctly. We'll get that today. And then with the VFDs, they're using those to do a very slow ramp over about 60 seconds. And they're also using them to control the speed so that they can get just the amount of flow that they want into their system. It's irrigation water system. So because we're using VFDs and because we're using a generator, we have included in the MCC active power filtration, active harmonic power filtration. It's essentially a bank of capacitors and a contactor hooked up. I guess it's in parallel with the line side filter, which is just a one-to-one transformer ahead of the drives. So this system's been running for at least 2 years with this configuration, and normally we'd see it come on, and as it's ramping and while the pumps are running, intermittently you'd hear these small contactors suck in to this capacitor bank for power filtration. And a lot of this is over my head, but I'm learning a lot about it as I go, working on it. 2 weeks ago, the trouble call came in. Hey, pump 1 shut off, and we don't know why, and it won't restart. Okay, so we go and look, and what had happened is pump 1 had tripped on a DC bus overvolt, which I'll see occasionally, but one of my checks there was, oh, okay, well, let's start up the generator and check all our voltages. So with the generator idling, we had good 480 volts, right on the money. And then as soon as the pump started, I watched the generator supply voltage climb up to about 600 volts. And then soon after, the DC bus voltage on the drive that we were operating also climbed. It reached the threshold for the DC overvoltage fault, and the drive tripped. At first, I thought, oh, got a generator problem. Something wrong with your generator. And I called my generator friend, who's a really smart guy, who helps me out a lot. And his guidance was, in a way that's true, because it's an older generator, and a newer generator would have faulted and shut off or opened its own breaker if the voltage had gotten that high. But he's saying because it's an older generator, the generator just didn't care. And he says it has to do with having large VFDs as your only load on the system connected to the generator. He said you'll get, the voltage will climb really high on the input side of the VFDs just because of the nature of the drives and harmonics, is how I remember it at least. And he said you need power filtration. I said, oh, well, that's good. We have power filtration. We have active power filtration. You know, there's an actual computer. It's monitoring everything. It's looking at everything. It even has Bluetooth. I'll show you that later. And judging on the quality of the power, it opens and closes those contactors to this capacitor bank. So after speaking with him, I then looked deeper into the active power filtration cabinet of the MCC. It's its own whole section. I was able to connect to each, there's two, one for each pump. I was able to connect to them with my phone with Bluetooth and get a little bit of data, but I wasn't really comfortable with how the app works and connects. So I wasn't entirely able to make sense of it. But I was able to see the very high voltage on the line in, and it kind of made me think, okay, I need to learn two things. I need to learn more about this active power filtration, and I don't really know where to start troubleshooting this piece of equipment, the active power filtration section. So the next day I went and contacted the manufacturer. They were incredibly helpful. They sent me a whole troubleshooting guide and packet to complete, fill out, email back to them. They think that it is the active power filtration's calibration could be out, or the capacitors themselves could be failing, and that could cause it. The fault, we were able to get it to happen sometimes and not always, which is my least favorite kind of fault. It's not every single time. And in fact, the last I heard, they're running one of the pumps right now without any difficulty. But we'll see when we get there if it actually is running. We ran it one time where we had 600 volts on the line in, but the drive's voltage regulator was able to keep its DC bus below fault thresholds. So even though the generator was doing crazy high voltage, the drive was just chugging along like everything was fine. So yeah, we'll see when we get there what's going on. Yeah, and with that guide packet, I'll be able to get a whole bunch of useful information to be able to send back to the filter manufacturer so they can see hopefully what's going on. And I'll probably end up learning something in the process there too. All right, we'll see you there.
One's running. Before I even bother getting out and getting all sweaty, let's take a look at this guide here. Manufacturing number, serial number, description, fault codes, when does it happen, system voltage and frequency, VFD manufacturer, motor horsepower, number of motors, load description, terminals line 1, line 2, line 3 are wired to incoming power, no load input voltage, no load output voltage, good, no load supply current, VFD output frequency, output power, loaded tuned circuit current, extra reactor, and then verify that your harmonic filter input terminals are wired to the correct place. Most passive filters will contain three-phase delta capacitors as shown in figure 12. Very large harmonic filters may have two turned circuits. As an example, if the passive harmonic filter has two tuned circuits, repeat the capacitive measurements on the second capacitor bank. I don't think we have a second capacitor. I think we just have one each. Usually you can check the capacity of the entire capacitor bank without removing or disconnecting capacitors from the filter. Determine where to make your measurements. If the filter contains capacitors with three terminals, three-phase delta capacitors, select any one capacitor from the bank to make your measurements on. You will only need to make your measurements on this. Make your measurements this single capacitor because all the capacitors will be wired up in parallel and all their capacitances will add together. Assign arbitrarily a letter A, B, and C to each of the three terminals on this capacitor. You'll be measuring between these terminals. If the filter contains capacitors of two terminals, those are single-phase capacitors. You'll need to measure the capacitance on each of the three cans. We'll go ahead and measure the capacitance. A to B, B to C, C to A. Good. No load testing. The no load voltages and currents can indicate the presence of a faulty or degraded component. Measuring no load filter input voltage and output voltage. Alright, we're going to be doing no load voltage testing. No load current. I have to force the contactor to stay engaged. I think I can do that with my Bluetooth. And then load testing, measuring the loaded system voltages and currents, making sure it's a stressful environment. Input terminal voltage. Try to operate the VFD load at the same conditions for each measurement. Tune circuit current, good. Tune circuit wires, yeah, okay. Interesting. Okay, pretty straightforward. We'll shut down, check all our fuses and capacitors. Then after we've checked all the fuses and capacitors, we'll power up and do our load and no load testing. Voltage is good, 480. These are 150 horse. Okay, there's VFD number 1. ACS 580 01 180A-4. 150 horsepower. That is the TCI KDR drive reactor. I think I'm just going to take pictures of him. We'll worry about that in a bit. Motor horsepower, 150 HP. It's, what is its FLA? I can pull that up real fast. 170. What do you call that? Centrifugal pump. Good. So terminals L1, L2, and L3 are wired to incoming power. L1, L2, and L3 are wired to incoming power. And terminals T2, T3, T1, T2, T3 are wired into drive incoming power. Good. Yes. Yes, we might as well do all this stuff on pump 1 as well. Even though oddly he's been working. Whew, cooking in here. Let's see here. L1, L2, L3. Good. T1, T2, T3. Good. P1 and P2. P1 and P2. Reactors inspected and pictures taken. Connections all look good. Let's get one of the nameplate. Good. P1 and P2. Capacitors inspected and pictures taken. That's in here. Visual inspection of capacitors. They have this expansion ring here for high pressure. They said to check that the terminals are all level. There's no bulging. That back one is a little bulged on one side. Not any more than the other one. So this is pump 1's active power filtration. And this is pump 2's active power filtration. Yeah, see the capacitors appear okay. Did they want photos and pictures taken? Yep. 2. Yes, pump 1 and pump 2. Section 4, table 2 and table 3. Tuned circuit fuse 1, 2 and 3. Where is tuned circuit fuse 1? Section 4. Let's just double check. Right there. Right ahead of the contactor. Okay. That's easy. I'll just make sure there's no voltage, because this pump was just running. Before I go getting really comfortable in here, just make sure there's no, these are all wired in parallel, so they're good. Yeah, I just want to make sure. I don't want to assume anything. That's good before I go sticking my head inside electrical enclosures. Generator's off, there's no power. Okay, let's check the fuses. So these are the tuned circuit fuses immediately ahead of the contactor, just downstream of the line reactor. Good. 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 And pump 2. Good. Good. And good. Okay. Sure. P1 and 2. P1 and 2. P1 and 2. Okay, section 4 to complete for. So we're going to do, this is P1, and we'll just say this is P2. That'll make it easier, even though it's not quite how they draw it. So just to double check, these are 3-phase capacitors. So they say, because they're all wired in parallel, what do they say here? They say, select any one capacitor from the bank and make your measurement on it. You only need to make measurements because all of them are wired in parallel and the capacitances will add together. Perfect. And fortunately, my 376 has capacitance function. Where we're going to put him? There maybe. Yeah, that looks good. And then we're in ohms, so we want to switch to microfarads. So then we go to 2. 147. 1 to 3. 147. 2 to 3. 147. Okay. Let's go note that. One four seven, 147, 147, and then we'll check pump 2. Okay, we'll do 2. 147. 147 and 147. Very good. So they're the same, at least. Done. No load input voltage, no load supply current. Okay, we're going to run it in hand. We're going to run the gen in hand. We're not going to call for a well pump or for a pump yet, but we will run it in hand. Let's see. 480. Good. They want me to take these measurements, section 5, input terminals and output terminals at the line reactor. So voltage between L1 and A1 and L2 and B1. Just verify that. Oh, L1, A1 is the same thing. Yeah, okay. So they want the voltage between the input and the output. Or not even. They want, yeah, they want the voltage from L1 to L2, L2 to L3, L3 to L1. And then they want the no load voltage from T1 to T2, T2 to T4. Yeah. This calls for gloves. Okay, first we're going to do L1, L2, L1, L2, 480, then L1, L3, 480, then L2, L3, 480. Good. Now we're going to do T1, T2, 480, T1, T3, 480, and then we're going to do T2, T3, 480. So notice when I'm in here in a rat's nest of live terminals, I only do one thing at a time. I move one hand, and then I move another hand. And I'm sure of where I'm moving my hand each time. I'm not reaching around casually. So I'll get one probe good, and I'll get another probe good. And then I'll take my reading, and then I'll remove. Just like that. Okay, so they were all 480. Write that down. Then they want current. Section 5, where do they want the current from? current on the input wires to the load reactor with no load. Okay? Essentially 0, 0.2, 0.3. Ah, I need to engage the contactor. Okay. So now we're going to connect to this bad boy with Bluetooth and engage the contactor. Alright, I got the factory password to force close that contactor. It's sucked in, and then... Oh, there it goes. $32, $32, $32. There we go. Just took a second. And now it's open. 32 amps. Alright, that's what we were after. Let's get the same thing for pump 2. That was pump 1. Let's get pump 2. Alright, here we go. Force close. 32, 31, 32. Back on auto load. Good. Very good. Okay, we're going to try and get it loaded now. Loaded supply current. What's nice is I think I have all this in my app here. So, line. Yeah, here's my line current and my THD percentage. Oh, that's so nice. I can just look at it right here as we load it up. And there's our input voltages, same thing. Loaded tuned circuit current. Where do I find that? Is that in my app? My loaded tuned circuit current would be right here. That'll be fun. Okay, we're gonna give it a shot, see if the fault occurs. I can just hold this in my hand. We're looking for these currents and percentages, these voltages, and the tuned circuit current loaded. And we can track the VFD output during all of that. So for this test, I'm just going to run this bad boy in local. There we go. It does a very slow ramp. There we go. Whoa, there goes the voltage. You can see the voltage climbing there. 525 at 3 hertz, 550, 550, 14 amps. And then a fault 3210. I got a picture there right before it faulted. There's the DC link over voltage. And we were at maybe 20 hertz when it happened. Okay, so that's kind of perfect. Dang, it didn't catch it in time. We're gonna have to do it again. All right, we'll do it again. We give the motor a 10-minute rest. Ready to do it all over again. This time, we're ready. Filter line, live. Filter okay. Filter load is live. Okay, here we go. Local control, 3, 2, 1. There it is. Snap a shot. That was at 3 hertz, 4 hertz. Contactor's not even sucked in. 8, 10, 22 hertz, 31 hertz. 31 hertz it tripped. It tripped and the contactor didn't suck in at all during any of that. Hertz. And catch the amps on the VFD. But then let's go to our, there it is. So we had input voltage 610, 600, 607. Current 18, THD 54, B phase 12, 18.1, 12.3, and that was 88.7%. And C phase was 15 amps, 15.5, and the 62.7. And then we had no loaded tune circuit voltage because the contactor wasn't closed. Do they want me, section 6, am I supposed to bypass that contactor for this test? Doesn't say if I'm supposed to fire that contactor. There's my tuned circuit. There's no load when that contactor's open though. Just wondering if I need to do one more test here, if I've got enough. Yeah. So much to learn. That is good enough for me. Let's shut down the gen, get this cover back on, talk about what we're going to do. Okay, we'll close it up. We'll put, what is it? 1 back in auto. Let it start up and run, make sure it's all good, and then we're done here and I can submit all this information to TCI. Pump 1 on the gen. I think it's about a 10-minute warm up and then it'll start ramping. check back in. Kind of suspicious. Like, it's easy for me to want to say, oh, the gen is the problem. But the fact that one of these runs just fine and the other does not makes it hard for me to say the generator's the problem. To me, that would be, neither of them would work in that case. So yeah, we'll wait for this to ramp up. It's ramping up. 2 hertz, 3 hertz, very slow ramp. And you can see our supply voltage is holding 480. We're up to 6 hertz, 7 hertz. Hertz. Hertz at 47 amps. 20 hertz. Voltage is holding at 480. So yeah, pump 1 appears good. Honestly, I just had a thought, a little nagging thought in my mind. I should meg pump 2, just to rule out a problem down in the motor. Yeah, I should meg pump 2. I'd feel pretty silly if it turns out the problem is just a shorted out motor. Let's do that. Let's just verify the basics. The basics that I do know, which is meg your motors. 1 is running good. Let's see if there's anything up with 2. Just to be sure, just to rule it out. You know, when I have a thought like that, it makes me want to check. Here's our line in, switch is open, load out, there works, and here's our equipment ground right there. And then that's a bad sign. Could it really be? Could it really be that basic that the motor is just shorted? Or could that be a secondary symptom? Could that be a secondary symptom of the problem up top? Okay, well, either way, let's drop down our scale. It is showing 0.12 ohms to earth on line 3. 1/10 of an ohm to earth on line 2. It's also showing low battery. And 0.8 ohm to earth on line 1. I am flabbergasted by that, and I'm going to go get my other meter to verify it with, just to say, because that would mean that there's a dead short in pump 2, like a dead short. And that would also mean I've been kind of wasting my time, perhaps, with this power filter stuff. I should still follow up with them. Okay, so just to remove any doubt, because I don't want to just throw the words dead shorted motor around, I've got my 376 here just with ohms, and I've got my disconnect switch open. There's no power on the line side, but the switch is open. These are the motor leads. They go down right to motor 2's pecker head right there. So, and here's its equipment ground coming back from there. 1.8 ohms. 1.8 ohms. 1.8 ohms. That is a dead shorted motor. 1.3 line to line. 1.5. Yeah, it is smoked. Might as well look in the peckerhead just to be sure. I don't see any ground faults along the way. Yeah, I might as well look in the peckerhead, but damn, that is bad news bears. This can stay wide open. And the last place to look is the peckerhead just to be sure. Because if there's a dead short in the peckerhead, then the motor might be okay and we can save it. But if there's no dead short or arcing in the peckerhead, then it's inside the windings of the motor and she's dead. And the customer's going to have to look at either rewinding it or replacing it. And then I need to figure out if this winding failure happened first and then we had the funky voltages and the power factor correction, the active power filter. Is that just a red herring? Or did something go wrong with the active power filter and its failure led to the failure of the motor? I think that's going to be brought on by talking with the active power filtration manufacturer and seeing what they say as far as the data I got. And if they say that data is all good and the power factor, active power filtration seems to be nominal, then to me it just points to a complete motor failure. I want to review my footage too and see what the amperage was doing on the drive output when we last ran it. But I'm not going to run it again because it's a dead short. I'm just going to break something. All right. Connect switch is open. We can open the peckerhead safely. Well, I'm really glad I went with my gut there and remembered the basics. Got troubles with the motor, Meggitt. I think initially I was distracted by the high voltage on the line side of the drive, and I'd never seen that before. And so I thought it was some kind of systemic issue and not an acute issue. And there could be more to this than meets the eye, but at this point, it seems pretty acute. And I can't deny that 2 of my meters saw a dead short inside of this thing. I mean, it's not even like 60,000 ohms or 100,000 ohms. It's just a full-on dead short. Okay, so here's our peckerhead. A little bit of nicking there. Doesn't smell like fire. Cables look good. Don't see any arcing. Little nick there, but she's okay. Alright. She's dead, Jim. Right there, you can see the amps. Just barely, or I can. 62 amps at about 5 or 6 hertz. 61, 62, 61, 60. We're at 5 hertz there, and we're at 59 amps. 59, 57, 7 amps. We're at 53 amps. There's 15 amps. 53, or sorry. Looks like 22 hertz at 54 amps. And then the fault there. So what I don't understand is how I can have a dead short in a motor connected to a VFD, and the VFD will run it and it won't trip on an overload. It will just feed the motor happily until I get a DC bus overvoltage fault, and my supply voltage, which is fed from a generator, so it's a very small system versus a utility system. My generator voltage climbs. The drive just gives it a little bit of amps and keeps it at a nice slow ramp, very slow ramp, but doesn't trip on a motor overload. I have a dead shorted motor that isn't overloading its starter. I don't understand why. But I'm going to find out. All right, guys. We'll see you on the next one. All right, well, before I leave, I had one other thought. Something I want to check. And I just want to verify the ground wire. Grounding. And it's kind of as I thought. Here's the ground coming back from the motor. It's connected well. This is all off, by the way. But what I don't see, unless that's it right there. Is this on? No. Okay. Oh yeah. No, it's grounded. Right back here. I don't know if you can see that. That big bolt right there. That's a ground wire that runs up right into the, what is that, line side of the drive. And he's landed on there. So the drive is grounded and bonded. So it's grounded to earth and it's bonded to the casing of the metal of the motor, casing of the motor. Just wanted to make sure there wasn't any weird grounding thing going on. Because yeah, now I've got to go into email land and get a bunch of emails sent to everybody letting them know what we found and what's going on. And I need to try and figure out with TCI if their active power filter is doing anything funny and if it could have caused this. And I need to figure out how an ABB drive can power up a motor that's shorted to ground and not overload. So much to learn. So much to learn. All right, see you next time.